I mentioned as best I can, I will record one of the lectures each week to post online for you to go back and review. And I mentioned, occasionally technical difficulties or user error might make that hard to do. And in fact, this week, changing microphones, I ended up without audio. And maybe in another week, I would just kind of end up not posting that video, but I do want to remake kind of the lecture from this week, because again, this is standard deviation. This is stuff that we're going to use so heavily that I do want to make this this material available for you to rehash and go back and pause and follow along. So I'm going to quickly kind of try to recreate on the blackboard here the process we went through in class. So if you were there in class, this is going to be completely redundant. But I do know a number of you felt that we went quickly through the material, and again, that's more okay to do, and you do have the ability to go back and rewatch. So I'm gonna try my best to kind of recreate what we did. So I'm gonna walk through the same examples, so what we're talking about here in chapter 3 is again trying to describe the variables in front of us, and how we in chapter 3 specifically we're talking about numerical measures. In chapter 2, and then what we turn to in chapter 4 is more visual. How do we visualize the data in front of us? But in chapter 3, we focus on two big concepts. Number one, where is the center of our data? And then how spread out is our data? Both of these contain quite valuable information for us. And so we're going to spend most of this discussion on the spread, because it's one of the more complicated concepts and more in our statistics here. So this idea of variance and standard deviation takes a few times to really start to sink in, and so I want to take our time and go through that kind of repeatedly, yeah, so it takes a few times to learn it, and number two, I think for the vast majority of you have covered things like the mean before. So we'll breeze through that quickly here, but there are other videos posted outlining those more specifically. When we want to use variance and standard deviation, we do need to calculate the mean, so we will go through that. So what I have here are three variables. Okay, I've put the data on number lines just to kind of so we can start thinking about kind of spread of variables, right? And so I have them listed here in black, red, and green. Note, of course, so this green one, if I were to try to match up the number lines, it would be way over here somewhere. Well, it'd be even further. It'd be off the board. So I've just kind of slid that back over. And again, so here are three variables. We're going to treat them as populations. So this is just a population of 4 people or 4. We'll put some context to it later. But it is the whole population. So that'll alter what specific equations we use. But as we'll talk about whether we're in population or sample, the concepts here are the same. So, yeah, if we wanted to summarize these variables, again, the first place we often start is where's the center of our data, or where's the middle of it? And so for that, we often use mean and median, and there are some other measures, but mean and median are really the two workhorses there. And as you'll see in some other videos, when we display both of those together, it also gives us more information. Things like the skew kind of come along with that. So the mean, now again, most of you have seen this many times, but the notation may be a little different. So this might be one of our first kind of entries into using, let me switch the color here, into using kind of this standard notation. And so when we want to talk about summing up, we're going to use the Greek capital sigma here. And so that all that tells us is that we want to sum up whatever's kind of to the right of this sum. So in our case, we're just going to sum up x, where x is the variable. So x in this case is 2, 3, 7, 12, right? A more traditional way to kind of outline this variable is in kind of the grid, or the, you know, in a data set, we'd see it more this way. So we're going to sum x and divide by capital N, where N is the number of observations. So in our case, for black here, it's 4. Let me just get rid of this x for now. Okay, and so we're taking the mean. And so, again, you've done this before. You're just adding all of them up and dividing by the number. So this, and let me just also say that this is, we refer to this as mu, or the Greek mu, which you can think of it as mu to pronounce it. And that's going to be our shorthand, or the letter we use to indicate the mean, and more specifically the population mean. So if you reference the material on mean, you'll know that x bar is for sample mean. Okay, so and one of the reasons we use this notation is that it's going to be easier than, or we're going to have to use things like the mean or summing over larger, more complicated things. And rather than having to write all of that out, it's easier to use this kind of notation. So hopefully you'll become more familiar with this as we go along. But this really means, okay, that we are just taking 2 plus 3 plus 7 plus 12 divided by 4, right? Which is, what is that? 5, 12, 12 plus 12 is 24. So we get 24 divided by 4, which is 6. So we have a mean of 6. So the black data here has a mean of 6. And we can quickly do that same thing for red and for green, right? And this is going to give us a way to talk about the middle of our data. I'm just going to do red first. So the red mean here is, so that's going to be 1, 3, 5, so that's 8, 20. So you can double check my math here, but that should be 30. Now this time it's divided by 5, right? So n is changed. N is now 5 instead of 4, and we still get a mean of 6. For the green set, I believe this is 348. Again, feel free to verify that. And this is divided by 4, which gives us 77. Okay, so now we have one way to talk about the middle of our data. Just to kind of rehash, we have talked about the median, right? And the median in this case is most straightforward in the red case, right? So the median just means, the median just means the center value, right? Especially once we've ordered the data. So in this case, we already have them ordered. They're on the number line. And so the red case is very straightforward, right? It's the middle value of 5. For the black and green, we have to rely on our concept of median being the middle between the two middle values, right? So there's an even number of values. So there is no middle direct value here. So we have to take kind of a halfway point between 3 and 7 for the black, right? And so what we do is we take literally the middle point, or the mean of 3 and 7, which is 5. Okay, so the mean is 5. Likewise, we take the middle of these the middle two values and find 77 as the mean. Sorry, as the median, which also happens to be the mean. Okay, so that was just a little extra practice on median. We won't use the median in our calculations here, but we will use the mean, and we'll rely heavily on the mean. Okay, so the mean, so we had mean of let's see, where do I want to, so we had a mean of, they'll just, mean is 77, and we had a mean of 6, hopefully that shows up, and then also a mean of 6 in here. Okay, so just so we can remember where we were. And so again, that gives us kind of an idea of where the center of our data is. But now turning to what I really want to dive into is, how do we talk about how spread out our data is, or how dispersed our data is? And to do that, we're going to rely on the idea of a deviation. And specifically a deviation from the mean. So how far do our observations deviate from the mean of our data? So let's just, so for instance, when we think about the value, I'm just going to redraw this down here so I can erase it when I want. So 2, 3, 7, and 12, and we have a mean of 6. That means that the 7, its deviation from the mean of 6 is only 1, right? So we have a deviation of 1, and that's much smaller than, say, the deviation from 6 or from 12, which is 6. Likewise, we have a deviation of, so this is 1, this is 6. We have a deviation of 3, but the way we calculate it, it will end up being -3, and then -4. I've got a lot of lines overlapping here, but hopefully it's clear that we're really just measuring how far away we are from the mean. Mathematically, how we're going to do that is we're going to think about, so x is 2, 3, 7, 12. Okay, and mathematically, the deviation from the mean is just simply x minus mu. Right, we're going to take the value of x and subtract off the mean. So that becomes 2 minus 6, or -4. 3 minus 6, or -3. 7 minus 6, 1, or 12 minus 6, 6. So now we have each of our observations now kind of turned no longer just the observation, but just relative to the mean. So some of our observations are less than the mean, some of them are greater than the mean. And we can quickly do that. I'm gonna quickly do that for the rest of for the red and the green. Okay, and you can always now you know where I'm headed. If you want to pause and just verify that you can do it, feel free to do that. So I'm just going to continue. You know, oftentimes when we have a data set, these wouldn't be right on top of each other. We'd have, you know, a different label and a different column for a different variable. But we're just going to kind of do them here for the sake of space. And this is going to be 1 minus 6 because we have the same mean. It's not always going to be the case, but it turns out in this case we do. Okay, that's going to be -5. I'll just -4. This is going to be -1, 4, and 6. Okay, and then lastly for green, we have 73, 74, 80, 81. And of course, this is now relative to the mean of the green. And so this is 73 minus 77, which is -4. We get -3, +3, and +4. Okay, so now all of these variables, we now have a way to discuss the observations relative to the mean, right? And so this might help us, again, and maybe I didn't reference this right away, but one thing we might want to talk about is which of these data or variables are more spread out, or which are least spread out, right? So we kind of have a center, or we know where the center of each of these are, 6, 6, and 77. But can we discuss which of these is more or less spread out? And we might visually be able to kind of pick up on that, and maybe you have some thoughts as to whether black or red is more spread out. But what we're trying to do here is develop kind of a numerical way to test that, or to quantify that. So we have the distances from the mean, and so a natural place you might think, or oftentimes a good place to start, is to maybe sum those up or take an average of them. So why don't we do that? What happens if we sum up the deviations from the mean? Well, black, we have -4, -3, so that's -7, and then we have +1 and 6, so that's +7, so it sums to 0. Okay, that seems concerning. And if we took a mean of that, the mean 0 divided by 4 is going to be 0. Okay, same thing is going to happen. So if I sum this up, -9, -10 plus 10 is 0. And the same thing is true for green. And in fact, if you've watched the video or read on the mean, this is always going to be true. The sum of the deviations from mean is always equal to 0. Right? And that's how mean works. If we start to mess with one of these values, say we start pulling, 73 downward, we change that observation to 63. Well, that's going to update the mean and also all of the deviations. So everything kind of gets updated anytime we move one of those observations, such that it's always the case that the sum of the deviations is equal to 0. So the sum of the deviations, or the average deviations, is not going to work for us. And the reason for that is the deviations, the negative deviations, completely balance out with the positive deviations. So we need to come up with a way to fix that. And the one that we're going to use is the squared deviations. So I'm going to make another column here, x minus mu, this time squared. That's hard to read. I'll redraw that. So x minus mu squared. Okay, and so we're just simply going to square the deviations. And what happens to a negative number when we square it? It becomes positive, right? And so this is going to eliminate that summation issue. So this becomes 16, right? Negative 4 becomes 16, -3 becomes 9, 1 is still 1, and 6 is 36. Okay, and we can do the same for the red. Becomes 25. 16, -1 is 1, 4 is 16, and 6 is 36. Okay, and then lastly, we get 16, 9, 9, and 16. Okay, so now we can think about adding up, or what we're actually going to do is take the average. So first, let's just sum these. So what is this? 16 plus 9 and 1 is 26. So 30. So 62. Again, always feel free to check my math. So we have a total of 62. It's no longer 0. So we've avoided that issue. Add up these reds. I believe this is 94. Okay, and then I'll just do the greens real quick. Now, we're not going to rely just on the sum, because if you remember, and this sums to 50, right? 25 plus 25. If you remember, our n's are different, right? So there's 5. N is equal to 5 for red and 4 for black. And we don't want to just simply say, red is more spread out simply because there's more observations. So we want to account for that. And so the way we're going to do that is we're going to take the average, actually. So we've already taken the sum, but what we need is the average. So let me just write out what we're doing. We are taking the average, which means adding them up. So we'll use that sigma notation. X minus mu squared. Okay, so when we use that sigma notation, we do everything kind of to the right of it. So we're going to take that deviation from the mean and square them, and then sum them up and divide by n. Okay, and so in our case, that becomes, that's 62 divided by 4, or 15.5. Okay, and same thing for the red. We sum them up. We take the squared deviations and then sum them up. That was that 94. So 94 divided by 5 this time, right? N is different, and we get 18.8. Now this time I've just written it as sigma squared, and that is the notation that we use. So just like with, well, that's on the last slide, but with the mean we used mu. For this calculation we use sigma squared, and this calculation is the variance. Okay, so it's taken us a while to get there, but we have arrived at one of kind of the two measures of spread. So the variance here is 18.8. The variance for black was 15.5, and let's just finish out the green one. That being, again, sigma squared, and that's the lowercase sigma. We've now used uppercase sigma for the summation and lowercase for sigma squared for variance. This is 50 divided by 4, right? Yeah, so that's 12.5. I think I did that right. So, so now we have a measure of variance for all three of these. And so a couple things to point out. We now have a way to compare across these three different variables. So we could say something like red has more variance. Red is more spread out, or tends to be more spread out than the black variable. And green is even less spread out. It's more tightly packed. And so now we have a way to kind of order these in terms of their variance. And especially when we're talking in the same kind of units. Okay, there are going to be concerns if we're not in the same unit. But here, assuming we're kind of in the same, maybe we're all talking in yards. Okay, so these are all deviations in the same units. Then we can definitely order these and say green is more compact. We're going to take it one step further. Okay, so I talked a lot about how standard deviation is going to pop up again and again throughout the class, and I've mentioned variance a little bit. We do use both. We use variance and standard deviation depending on what we're calculating. But especially concerning or considering describing a variable, it's much more common to talk in terms of standard deviation. And we are only one little step away from standard deviation. So let me just, I'm just going to write this down here. So a big takeaway or something to bear in mind is that let's see, let's do it this way. So the variance, the square root of the variance is the standard deviation. Okay, so or another way to think about that is, what did we just call variance? We called it sigma squared. The square root of sigma squared is just sigma. Okay, so the standard deviation we refer to as sigma, or you'll see it written that way. People will verbally often call it standard deviation, but you'll see it written as sigma. And so all we have to do here is take the square root of our variance. So let me just do that quick. I think I have enough space. So the square root of 15.5 is, and just check my cheat sheet here, that's 3.94. So the standard deviation is 3.94. And I'll quickly just do red and green. So the square root, again, to find the standard deviation, the square root of 18.8 is, and now before I give you the answer, we should know, or at least be able to anticipate what the square root of 18.8 is going to be relative to what we just did with the black. So the black standard deviation was 3.94. because it was the square root of 15.5. Now, when I take a square root of a larger number, it's going to be a larger number. Okay, so when I take the square root, it doesn't reorder anything, and that's an important aspect here. In that, one of the goals or one of the uses of that variance was to keep or to get an order of kind of which variable was more or less spread out. Standard deviation carries with it that same ordering, right? If you take the square root of 25, it's larger than the square root of 16. So we don't lose that ordering. And so we can use either one, variance or standard deviation, to do that same kind of comparison across variables. And then lastly, this is 3.54. Okay, so green remains the smallest in standard deviation as it was in variance. So, okay. I'm next going to talk about, or in a little bit, I'm going to talk about why we may rely more on standard deviation, or one of the benefits of standard deviation relative to variance. But first, I want to address one common thought that students often have, and that is so as we were doing this, what did we really do? We found the mean. Okay, we found the mean of all of our variables. Then we thought about each of the observations as a deviation from the mean. Okay, we had an issue that they summed to 0, which means we couldn't take an average of that. So to fix that, we squared them. Okay, and then we were able to take an average. Right? So this variance here is just the average of the squared deviations. And again, one of the reasons we went with the squared was to alleviate this sum to 0. And so a common question, and some of you are likely having that, is why not use something like the absolute value? Okay, so instead of squaring, what if we just took the absolute value of all these, right? Because again, that's going to fix the negative issue. Recall, the absolute value of -4 is simply 4. And so that would also fix the issue. And you're on the right path, and you're asking good questions if that's coming up in your mind. And in fact, using the absolute value or the deviation, the absolute value of the deviations is a method that is used in statistics, just not as common as the squared deviations. And there are a couple of reasons for that. As we progress through the class, you'll notice some pretty powerful tools that we're able to use using this standard deviation method. So it turns out that this taking the squared deviations ends up being pretty helpful, or leads to some pretty powerful tools. So that's why we focus in on those. Again, there are reasons and there are methods that do use the absolute value. And one thing to be aware of is that when we do this, the standard deviation method, or the method that we're doing here where we square the deviations, that does put extra weight, or it weights heavily kind of large deviations, right? So you can see what happens. So let's see, here's our deviations, and they range from -4 to 6. When we jump over to the squared deviations, you see the ones in the middle, a deviation of 1 still stays at 1. -3 gets a little bigger, it's 9. But this 6 all of a sudden becomes 36, so it gets quite large. Okay, and so what that means is that standard deviation heavily weights large deviations. And so there are some methods which try to avoid that, and that's where that absolute value methods come into play. Okay, if you're feeling a little overwhelmed about this absolute value idea, I'm not going to be testing you on that. I just wanted to kind of answer some questions about that. Another reason why we tend to go with the standard deviation is, as we'll see, at the end of this discussion, it carries with it some pretty useful descriptive abilities as well through the empirical rule. And then lastly, it is important to remember that there was a time where we all didn't have supercomputers in our pockets, and computational power was important. And it turns out that the squared deviations method is computationally nice. And so at a time when statistics, many methods were being developed, making sure that they were able to be done, relatively quickly or easily by hand even, or with pretty primitive computational power was important. So it did kind of lead us down the direction of leaning more on those methods. And lastly, I just point out that if you do continue your statistics studies, so for instance, here at Hamlin in the business school, there's an econometrics course, you will delve into some more of these questions, and you'll spend probably more time than you would like looking at concepts such as BLUE, or why some of these methods are, or why the standard deviation leads to what we call the best linear unbiased method, and so why we favor those methods. And so if that's of interest to you, know that there are classes where we would dig even deeper into these concepts. So all of that is to say, if you have these questions as to why don't we use absolute value instead of this, you're thinking about it in the right way, in that oftentimes there's more than one way to kind of accomplish what we're trying to do in statistics, and there's often, or hopefully there's a reason why we go about it one way, but feel free to ask those questions, and even if it's something we're not digging into, I'm more than willing to chat with you about it. Yeah. So jumping back to more of what the other big thing I want to talk about is variance compared to standard deviation. And so I want to start by saying, now we have what we need to describe a variable. We can say, I have this red variable, it's got a mean of 6 and a variance of 18.8. And that is a fully sufficient way to describe a variable, talking about its center and its spread. What you are more likely to hear from someone is, I have a mean of 6 and a standard deviation of 4.34. And that's typically how you would hear it referred to. And we're going to walk through an example as to why, kind of the big reason as to why we would stick with standard deviation for describing. And that's going to center around the units that we're in. So, if I can get this come back online. So we're going to think about. Just having a little bit of technical difficulties. So we're going to think about an example where we're going to use the same number. We're going to focus in on the black variable here and say that we had, this is actually, we're going to measure it, it's measured in yards. So the example I used in class, I said that we were spitting watermelon seeds. Okay. And let me just disconnect this, and I'll set it up while we're talking about it. But that's weird. But instead of the 2, 3, 7, and 12 just being random numbers, those are now the yards at which one of our 4 people, or each of the 4 people, can spit a watermelon seed. And so we've done our calculation, and we're able to describe our variable in terms of yards, and there we go. Back up and running. Okay. So let me get rid of the black and the green, and let's just focus in on the black here. And Oh man, the computer is really not liking this. Okay, so I might have, there we go. Okay, apologies for that. So now we have our black variable. Now what I want to do is say, what if we want to talk about this? So this is in yards. Okay, and we found out that we had a mean of 6. And we also knew that we had a variance. Let's just put it as sigma squared. Variance was, let's remind ourselves what it was, way over here, 15.5. 15.5. And sigma, or the standard deviation, was 3.94. Okay, so that was the way we were able to describe our variable. But this is in yards. Okay, so when let's change colors, let's call it yellow. Now I want to talk about it in feet. And this is something we end up doing quite often in statistics, is that we want to alter the units that we work in, right? So maybe we were working in, we have all this data in miles, but then we needed to present it to our Canadian counterparts, and so we have to change it to kilometers. Okay, so we have to change our units. Or we have data in thousands of dollars, and we want to put that into dollars, or vice versa. So it's not uncommon that we have to do these unit changes, and maybe we do it simply because it's going to display better on a graph or something. So if we're in feet, and we try to write that down, I think I'm noticing there's a limit on the time that this program wants to work. So if we change that to feet, this 2 becomes 6, 3 becomes 9, 21, and 36. Okay, so this is presenting the same watermelon spitting distance, right? Nothing's changed. We haven't even redone the analysis. This is just altering the units. And so we could find the mean again, right? If we want to do this whole analysis, we need to find the mean. Okay, and that's divided by 4, and that should be what is this, 15, 36, so 72 divided by 4, which is 18, I think. And so we now have a mean of 18. Okay, so pretty easy to refine kind of the center of our data. Now, if we want to turn and find the variance in a measure of spread, we can simply just go through the same process we did before. So now we have 6, 9, 21, 36. Do x minus mu. And this becomes negative 12, negative 9, 3, and 18. Again, we could double check. That looks like it would sum to 0. And then one more step, right? So to find the variance, we're going to square those deviations. This becomes 144, 81, 9, and 324. And then lastly, we take the average of those deviations. Okay, and so where do I want to do that? So this sums to I think it's 558. Just to help us along our math here, 558 divided by 4 is 139.5. Okay, so there we have the variance. So we have the variance of 139.5. And if we take the square root of that, we have the standard deviation. I believe it's 11.81 if we round it. Okay, and you can walk through that again if you'd like to double check my math and just verify how we go about that. But we now have, let me just point out, we have a measure of variance and standard deviation for both of these, and all we've done is change the units. So we have our measures of the center of the data and how spread out the data is. And what I want to highlight here is that if you notice, variance has started to grow quite quickly. Okay, so we scaled up from 6 to 18 in mean, but we've seen variance already reach well into 139 and in the mid 100s, whereas standard deviation has scaled up but not as quickly, and there's a reason for that. And that is that if we think about what units we are in this whole time, and let me think about the best way to display this. No, this last one was very busy. But let's pick another color. Okay, so we were in yards. And so our measurements were in yards, mean of 6 yards. Our standard deviation, or sorry, our deviations were in yards. But when we fixed our issue of trying to get rid of the negative numbers, we squared this. Okay, so we all of a sudden went into yards squared. Off the screen. Yard, that's supposed to be a 2, but let's move it down here. I know this is kind of written all over the place, but we're into yards squared. Okay, and what that's caused is kind of a ballooning of our values. And so we are in yards squared. When we take that square root, the units get square rooted as well, and we return back to yards. Okay, so standard deviation returns back to the units in which our variable is kept. Again, just walk through that again. Here we're in feet. Okay, we're still in feet, or our x is in feet. Our deviations from the mean are in feet. When we square them, we become feet squared. And then it's not until we go back to taking the square root that, why did I put yt? Here we return back to feet. So we're actually, keep jumping back and forth. Okay, so we're actually in feet squared for variance and feet for standard deviation. And so the variance ends up ballooning at the rate of the change in units squared. So what did we actually do? We did a 6 to 18 was we multiplied by 3. Right, we scaled everything up by 3. And so when we do so that carries with it, so for instance, 11.81 divided by 3.94 is, barring a little rounding, that's 3. And so the standard deviation scaled up the same rate or the same amount that our units did. But as you can probably notice, let me see, 139.5, if we divide that by 15.5, right, if we divide this by way up there, we look at how the variance has changed, that's obviously going to be larger than 3, right? You can probably just sense that. And in fact, if you do the math, what you'll see is that it comes out as 9. And that makes sense, again, because our units are squared, and so really we've scaled up by 3 squared, or 9. So the variance has ballooned quicker than our units or the standard deviation does. And again, that's not as... so one of the benefits of standard deviation is that it continues to make sense and it fits in with our current units, no matter what they are. Variance loses a connection to that, and in fact, it can become quite cumbersome. In the video, another video I have posted here, I do an example where we're talking about a change from thousands of dollars to dollars, and that's a unit change of 1,000. And so if we think about what we just learned, variance scales up by 1,000 squared, which 1,000 of thousands is 1,000,000. And so all of a sudden you have variance in the millions. And so it can become quite cumbersome to work with. And it also doesn't carry with kind of an intuitive sense as to this, to what we can learn from just that value. So the standard deviation tells us a little bit more in terms of describing the variable. So that's kind of the big, in terms of descriptive power, which again is what we're focusing in here on chapter 3. That's kind of the main reason we stick with standard deviation to describe a variable. In addition, as you learn in chapter 3, the empirical rule comes into play here, where if we know some other things about the variable, specifically if we know it's a normal variable or normal distribution, in that or a bell-shaped curve. I can flip pages here. We learn extra information if we have the mean and the standard deviation. So I think my, oh, there we go. Oh, I think the iPad might be it's at its wit's ends here, but there's an additional video on the empirical rule, and just to point out again that brings with it descriptive power. If we can say it's a normal variable, the mean is, mean of 27 and a standard deviation of 4, that carries with it an incredible amount of descriptive power. And so that is also, again, why you tend to see standard deviation used. And as we'll see as we go through the course, the normal distribution pops up quite often depending on the methods that we're working with. Yeah, so I mentioned in class that this standard deviation, this area of the text is where I will likely remind you to return to a number of times throughout the semester. And as I mentioned, if you had most of you are working with the online book, but if you had the hard copy, I would tell you to kind of dog-ear this page or this set of pages where standard deviation is first introduced, because again, this is a concept that oftentimes becomes more illuminated the second and third time you work through it. So hopefully my goal is that you understand how to compute it and a little bit of the why, but you likely don't feel the power of it yet. And so when we get into using it for more elaborate techniques, it'll be a good time to come back, kind of reread it and say, oh, so this, the ability to square it does this, or we'll talk more about it at that point. But this is that part that I made reference to that we'll probably come back and look at. Okay, so yeah, check out the other videos that I have posted, but hopefully this gives you kind of that example from lecture to be able to go back, pause, and rework out these examples.